Alright, it's time for silver. Let's get into it. One of you guys asked for it in the comments yesterday, and I'm sorry to get it out earlier, but I've been really busy for the past 2 weeks. But today we're gonna do it, okay? I'm gonna make it up to you guys. Also, a bunch of you guys have been saying that my audio quality is not that good, so I tried bringing my microphone up a little bit, so we'll see if that improves it. You guys let me know. You guys clearly will like it when I go real close to the microphone, PewDiePie style. You like that? You like that? No? Alright, let's just get into it. Why not? Why not? Hello everybody, I'm Kara, and today we are going to be doing a live solve for the USACO 2021 February contest silver, and we're going to start with comfortable cows. Epic. It is same as the bronze one, hopefully, no kidding. Alright, so farming the Hodges pastures can be regarded as a large 2D square. Okay, so this is the same as the bronze one, okay, and you basically have cows in each one, and you're adding them one by one. And basically it's comfortable if it is horizontally or vertically adjacent to exactly 3 other cows. Alright. Unfortunately, cows that are too comfortable tend to lag in their milk production, okay? And the farmer John wants to add more cows until no cow, including the one that he adds, is comfortable, alright? So for each I in range 1 to n, output the minimum number of cows that farmer Nahaj needs to add until none of them are comfortable for each, like, I. Okay. So you got this, and then basically for each one you say how many you have to add. Alright, let's just try photoshopping this boy, and we'll see. Alright, so basically we got our coordinate plane, right? And essentially we first add in 0, 1. So nobody is comfortable, so we're chilling. Then, oh, that's not 0, 1, what the heck? Bruh, 0, 1, that's how we do XY coordinates. And then we got 1, 0, so nobody's comfortable still. 1, 1, nobody's comfortable. 1, 2, now this dude is comfortable. So now we gotta add 1 over there. Okay? Then we put 1 at 2, comma what? Did I? No, I didn't. I messed up again. Oh my god. Okay, so 1, comma 2 is there, and we want to have to add 1 there, and then 2, comma 1, so we add there, and then now nobody's comfortable anymore, so we're chilling. Then we got 2, 2. Nobody is comfortable. Then we got 3, 1, so now this guy is comfortable, so we gotta add someone there. Is anybody else comfortable? Doesn't seem like it. And then we got 3, 2, so there. Now is anybody comfortable? Still nobody's comfortable? Wait, what? No, somebody has to be comfortable at 3, 1. Okay, I think I messed up somewhere. Why is this? Who's not comfortable? Oh, 2, 0. Oh yeah, okay, wait, what? Why did I have a 2, 0 for no reason? Okay. So essentially we have this, so then this guy is not comfortable anymore, so we gotta add 1 more, right? And then we add 3, 2. If we add 3, 2, what does that even change? Oh, this guy's, okay, then we have to add this guy, right? And then we add 4, 1. So now this guy, we need to add that, and then we had to add that. Okay. So then these 4 are the ones that we had to add for this, and that's why it's 4. Okay. So essentially the idea is when we add somebody, well, okay, I guess, So I guess the first thing to notice, right, is that like whenever you get to like when you add somebody, it can only affect the guys next to it, right? Like this guy can only affect these 4 guys, right? It can only add 1 more adjacent guy to those. Okay, so essentially when we add it, we only had to check those 4, right? But then if we find somebody who's comfortable, then we have to add another guy, and then that guy could affect a bunch of guys, right? And then we had to keep doing that until we are done. But if you do that every single time, right, then it's like n squared, because like each time you could add like a bunch of counts. Wait, actually? Huh. Well, we need to not repeat work, right? Like if we know, okay, so let's see. So let's mark the guys that are not like actually added. So we'll mark like guys that are not actually added, but we want to add them in order to get everybody not comfortable. So essentially we know that this guy will have to get added to make this guy uncomfortable no matter what, right? There's no way for this guy to not get added. Like, there's no way for this guy not to get added and for this guy to become uncomfortable, right? Because these guys are already fixed, right? So essentially, the only way where this guy doesn't need to be added is if we put somebody on it, right? Which is why it goes from 1 to 0. Okay, so that makes sense. Yeah, so essentially, like, we could basically treat these guys as like already placed, right? Because they're never gonna change. They're either gonna get filled in, like, and be like actual cows that have already been placed, or they're gonna be cows that we need to place like additionally, right? There's no way for them to like get like taken out fully, right? So we can just treat them as actual cows. Okay, that sounds fine. Okay, and then every time we add a cow, we just check its neighbors, right? So if we're doing 2 comma 1, we did that 2 comma 2, right? We only have to check these 2. Neither of them are comfortable, so we're good. Then if we do 3, 1, then we see that this neighbor is uncomfortable, so we add 1 there. We check this guy's neighbors. Nobody uncomfortable, so we're good. Okay, so basically every time you find a comfortable guy, then you have to add 1 to the number of, well, okay, you have to try adding this, and if it's already like a potential guy, right, like the circle one, and we add somebody like an actual guy in here, then it's -1, right? But if there's nobody there, right, the nobody here, and we are adding a completely new potential guy, then we have to add 1, right? So I think like, so right, it goes from 0 to 1 when we add 3, 1, right? And then when we add 3, 2, then this guy becomes uncomfortable, so we add a potential here, so now it goes from 1 to 2. And then when we go to over here, right, 4, 1, then this guy gets a potential, but now there's this guy, this potential is comfortable now, so we have to add 1 there, right? And then, so we added 2, in which case now we went from 2 to 4, and our answer is 4. Okay, so essentially our algorithm, okay, so basically we just need to keep track of which ones are like real cows and which ones are potential cows, right? But then like we treat all of them the same when we're like adding new ones, basically. Actually, no, not really. They're kind of different. Okay, what's the main difference? The only reason you would care whether it's a real cow or a fake cow is because if it's already a real cow, then if it's already there, you don't add more, right? Because like let's just say that I don't know, we put one guy here, right? Then this guy would be uncomfortable. No, actually, huh? Well, I guess we would never actually try to add it. We'll never try to add it on top of something else, so it doesn't really matter. So the only time we care whether it's potential or not is if we fill in a potential with an actual, right? And then in that case, our thing goes down because we no longer have to add that separately. Okay, so how could we do this efficiently? So I guess the first step is like when you add a guy, you first check if like the guy himself is uncomfortable, right? Like if we have like 3 guys here, then when we add a new guy in, we first check, okay, am I uncomfortable? Yes, I am. I have 3 guys, so let's add the remainder one over here, right? And then when we add that guy, we check, oh, is this guy comfortable? But he's not, right? Because he only has 1 adjacent guy. And then we just check his neighbors, right? Does adding me in make this guy uncomfortable? I mean, make him comfortable? No. So then we don't have to like add anything more. Okay, that seems legit. Let us code this up. All right, let's do it in Python this time because if it doesn't work, then we'll go to C++. I hope I do not regret this, but let us just try it, okay? So we'll call it like Comfort Silver. Why not? Okay, so we want to be pretty careful about this because if we're not careful about this, we will be spending forever coding because this does not seem very fun. Okay, so first thing we gotta do is okay, well let's first read in our stuff so we could, okay, let's just first read in our stuff though so we don't have to worry about that later. Okay, and then for I in range n, what will we do? Well, we can do x comma y is equal to map int input dot strip dot split. Okay, so now we got our xy coordinates of the guy to be added, and now we have to keep track of the guys that have been added, or like the potentials that have been added, right? So like potential doesn't mean the cow that needs to be added but haven't been added already. Okay, so grid, and we'll just make this a array of numbered boys, and it'll just store how many are adjacent to it. So I guess like -1 will mean that it's not occupied, I guess. So times n for I in range n. Okay, so basically we have the same, like, basically every time you add something, it's the same concept, right? You basically first add it, you check if it's comfortable, and if it's comfortable, then you have to add somebody to make it uncomfortable, right? So we're probably gonna have to use some kind of recursion here, right? Because we check and then we have to add, like call the same function. So we'll make our own def add, and then we'll put like x comma y, right? Okay, so it doesn't matter if we're adding a potential or a not potential. Well, I guess we'll just mark it as potential or not potential before we call add, so we don't have to worry about it too much. Because the only person who's going to be actually adding like real ones is this for loop over here. So essentially, when we add a guy, we basically do grid, or basically, okay, so we have to look at all 4 around it and figure out how many are adjacent to myself. So I think the best way to do this is to have like an add list, and we'll just have some tuples 0, 1, -1. I mean 0, -1, and 1, 0, and -1, 0. Okay. So we'll just do for p in add, we'll basically say next p is equal to x, or next x is equal to x plus p0, and next y is equal to y plus p1. Oh, I see. Wait, what? What's the problem? Oh, okay. And then if next x, so Actually, this can't just be n. Okay, this has to be like 1,000, right? Well, we'll make it like 1,001 because the new cow that we add has to be at least like 1 next to, like, it has to be within 1 of a of like 0 to 1,000. So we probably had to do 1 to 1,002 because we could do -1 as a coordinate 2. 1,002. Okay, if next x is like what, greater than 1,001, or next y. Actually, wait, that's not true though. It could keep going out, right? Okay, I'm just gonna make it a lot bigger just in case. I don't think it could keep going out, but just in case. And we don't even need to check then, I think. Okay, so if grid next x comma next y is greater than or equal to 0, that means it is occupied, in which case we want to do, well, okay, so we'll set grid xy equals 0, and then we'll do grid xy plus equal 1. Okay, so now we know how many people are adjacent to ourselves, in which case we basically want to say if our, let's see, if grid xy equal 3, then we have to add 1 to the one that doesn't already have a cow in it, right? So, why don't we just define another thing that says def add remaining, right? So essentially this will just go through the it'll just go through the thing assuming that it has 3 neighbors, and then find the one that's not actually, like, doesn't have a cow yet, and then add it in. So for this, if it is actually less than 0, which means that it doesn't already have a cow, then we want to add in that cow. So we want to do add next x comma next y. All right. Okay, and then we want to do add remaining x comma y. All right. Now we basically had to go through all of the ones around us, and we have to add one to their adjacency, right? Because all of them are now adjacent to one guy. So we go here, we do that if it is greater than or equal to 0, then we do grid next x next y plus equals 1, right? Because now we're adding one adjacent to it. And we want to do if grid next x next y is equal to 3, then we want to do add remaining next x comma next y. All right. And we should just set like potential to true, right? Well, what should, oh, okay, so for by default we'll set potential to false, right? So we'll have a array of potential just telling us whether each grid point is a potential cow or a real cow, right? And then every time we add something, like, we'll set the real cow to be potential to true. So we'll say false, and over here we'll, before we do anything with it, we'll do potential xy is equal to true. Real, we'll call it real. Real xy is true. And then we will add it. Add x comma y. And basically if, well, here we could just say if, wait, do we even care if it's potential or real? So if the grid xy is already greater than 0, greater than or equal to 0, that means that we've already added it as a potential, right? Which means that we should just, in that case, we should just, what, minus it, right? So we'll keep our total. We need to keep track of our total, right? So total to add, right? Or we should probably keep it at top. Top is equal to 0, right? So if we find one that's already been placed and now we're actually filling it in with the real one, we want to subtract from our total, right? So total minus equals 1, and then we add it, okay. So every time add remaining is called, then we want to actually, then we want to increase tot, right? Because that means we have to add a potential here. So tot plus equals 1, or we should do global tot. Okay. And then theoretically this should work if we just like add it, and then, do we even need potential? Real or anything? Yeah, we don't even need this. What the heck? Okay, we don't even need this. Alright. So if that is true, then we just do print top. Alright, let's try it. I doubt it's gonna work the first. There's a 0% chance of that happening, but we're gonna try it anyways because we're cool. Dang. What? It actually doesn't work? What the heck? Alright, I mean, we'll see. We'll see about that. Let's try it. Alright, moment of truth. It'll guarantee not work, but we could at least see how many we got wrong. If we got a lot wrong, I'm gonna be very sad. Yeah, bro, we didn't even get the second one right. What? Okay, so let us make sure our logic is correct. So essentially we're doing add xy, right? So then it goes in, it checks, okay, am I comfortable? If I'm comfortable, then we want to add our remaining dude, okay? And then if, okay, so it goes through, so when we add remaining, then it adds one, okay, because we're for sure going to have to add a potential. And then it goes through each possible next x or next y. And if it is less than 0, then we want to add it. Okay. And then it goes here, it sets it to 0. And then it goes through each of its dudes. If it is greater than or equal to 0, then it add 1 to it. Okay. And if it is greater than or equal to 3, or equal to 3, oh wait, okay, so I should probably not do this here because that doesn't make any sense. Okay. Bro, I should do it here before I do any adding or anything. Oh my god, dude, that makes so much more sense. Holy. Okay, let's try that. Okay, plus work, I beg. Come on. Come on, you gotta know it's gonna work, right? Plus. Hey, let's go. Okay. So now we just need to get rid of these annoying like error messages. So that shouldn't be too hard. Okay, so we got the right algorithm. That's good. So I think we just make this really big. It should be fine, but we can't make it that big, I guess. So let's do 5,000 and 5,000. See if that works. But there is a very good chance that Python is just too slow for this nonsense. God dang it. And worst comes to worst, we could just store it in a map. So if that is not working, then we could fix it using a map. Okay, so I guess Python is just troll, so let us do it using C++. Because this should theoretically not take that long because, like, you're basically adding each one once, and you can never add to the same grid, like, more than once, right? So, I'm pretty sure that this won't time out in C++, so it should be fine. Right, because basically for every three things you have, you can only add like one more thing, right? Like there's no way to make it like double how much you have, so it can't be more than 2n things that we're adding. So I think it's just Python being troll. Oh yeah, let's move this to C++ and use a map. Or why don't we just use a map? Okay, so we will do grid is like that. And how do we check if the map has it already? And then if we just want to check, we just say like if xy is in grid, or next x, comma, next y is in grid. Okay, I'll just convert this all to dictionary and we'll see if it works. Okay, let's try that. So it times out on that, but will it error out on anything? Well, how did it get an error? What the heck? Oh, maybe it's like recursion overflow or something? How did that even happen though? Okay, you know what? We're just doing C++. God dang it, dude. I'm pretty sure that it is a problem with Python's recursion limit nonsense. So, and I'm pretty sure like the answers it can't be more than 2n. So as long like it should be like within the time limit. So I'm pretty sure it's just Python being bad. So let's just do C++. Okay, we finally converted it to C++. Please work. Nope. What? Oops. Semicolons kind of bad. Not gonna lie. All right, let's try this. Whoops. C out top. Let's go. Okay. Very nice. Okay, will it work in C++? Oh, I'm so triggered now. God dang it. I'm never using Python again for Silver if it works. Oh, holy moly, dude. Bro, no, what? Okay, so that times out. Oh, bro, that's so... Okay, huh. Wait, but 8 still works. You literally get more points for doing the same thing. Wait, okay, maybe I'm... Okay, I'm probably doing some extra work somewhere. Let's see. Huh, maybe the find slow? I'm pretty sure it shouldn't be that bad. Yeah, maybe finding stuff in a map is slow, but that doesn't make sense, though. Does it? I don't know. Let's try doing the array version. Well, can we do array version though? I don't know. Oh, what? Oh, I had to set all of it to something good at the beginning. Oh, finally, dude. Holy, that's so stupid, dude. That implementation just yucky. Holy. Why did I do that to myself? You know what? We're not doing Python for Silver anymore. God dang it. Okay, you know what? Moving on. I'm so triggered. Bruh. That really took me like 1.5 hours just to code that nonsense up. Bruh. Okay, hopefully the next one will go a little bit smoother. Hopefully, we'll see. Alright, problem number 2, Year of the Cow, please be better. Farmer John's cows are excited to learn that Chinese New Year was recently celebrated, ushering in the year of the ox, always a bovine favorite, of course. As we know, the zodiac animals for the Chinese calendar years follow a 12-year cycle. Ox, tiger, okay, so this is basic. Oh, what? They have like a bunch of the same stuff. Oh, I guess they're just reusing problem statements, very nice. So basically, she wants to take advantage of a time portal. Oh, okay, so that's very different. To visit N of her famous bovine ancestors, okay. What's 0x? Oh, just, oh, hex, okay. Alright, and unfortunately, time travel makes her quite queasy, and she would prefer to make at most K jumps through time, okay? So basically, she wants to find the minimum number of years that will take her to visit all her ancestors and return to the present year with at most K total jumps, okay? So she doesn't have to use a time portal, okay? And they connect the first day of each year, okay? Oh, huh, okay. So, each of them give how many years ago they live. Okay, so currently we are, wait, okay, this is like 10 to the 5 approximately. So, ox year is every 12 years, and are we currently in an ox year? Oh yeah, so we're currently in an ox year, so that's good. And essentially she could, okay, so she could travel 48 years, wait 12 years, then, okay. So essentially, the cows are on this timeline, right? We could basically sort them, and we got like 101 years ago, 100 years ago, then 85 years ago, then 46 years ago, then 95 years ago. Okay. Wait, what? That's not how you do it? Okay, so we got 101, 100, 80, 95, 85, and 46. Okay. So essentially, the strat according to this thing is to so you basically go here, right, and you go till there, and then it says to go to 108, then go through all of these, and then go um back another time, and then go through here. Okay. So essentially, she has to hit every single like 12 that includes a cow at least once, right? Because she can't not go through a length of 12, right? She could only move in like these segments of 12, right? So essentially, we can first draw out her segments of 12, right? So we first draw out segments of 12. Well, you could go to any time in the past, right? Okay, so essentially she needs to hit this one, she needs to hit this one, and she needs to hit this one. Now, because k is 3, right, she could do jump, 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 right? And then, wait, what? So that's one jump, that's two jumps. Wait, what? Isn't that four jumps? Oh, so 108 hits all of these guys. Oh, okay, so, yeah, because these guys are, oh, so this is adjacent, these are touching. Oh, okay, so you don't need to do that jump, that's what it's saying. And then you jump back to present. Okay. So essentially the reason why this works is because these two are together, so obviously you would want to do those together. Okay, so basically if you have like, okay, so ones that are joined together, obviously you should do together, right? There's literally no point to like go here and then like jump back here, right? And then go, right? So if they're right next to each other, you might as well just do them together, right? Okay. Then you look at ones that are like spaced out once, right? So now if you're still not like after combining all the guys that are like right next to each other and you still don't have enough jumps to do that, then you have to then you basically have to combine ones that are two apart, right? And then you want to combine things that are three apart and so on and so forth until you're down to the right number of jumps, right? So how do you do that fast? So essentially you can have like approximately you can have 10 to the 5 of these like little strips, right? And you can basically count out like how far apart adjacent strips are, right? So these you could count how far these two strips are and these two strips are apart, right? And then and then basically you just close up the like okay, so essentially each gap, okay, so let's just say these are three separate gaps, right? So one, two, three. So essentially you'd have to go one, two, three, four. So essentially your number of jumps is equal to the number of gaps, or plus two. Gaps plus two. So essentially, if you want to bring down, then basically every time you close a gap, right, like you combine two, that takes away one gap, right? And that basically takes away one jump. So essentially, you just want to take away, if okay, so if you have n, right, or let's just say you have like g gaps and k jumps, right? Then you want to take away the top g minus k jumps, right? Because right here we have, or sorry, g minus k plus 2, right? Because essentially here we have two gaps and we have k is equal to 3, and essentially we had to take away one edge, right? And that was just a edge of 0. So essentially we can just do the same thing. And every time you take away a gap, that's you basically have to add that into your time, right? So essentially each of these counts as 12, right? So if you have 12 gaps, you got to take 144 time to go through all of them. But then if you add in a gap of 12, then if you combine the two, that means you're just going through them at the same time. So you'd have to cross that gap, in which case you have to add the length of the gap. So essentially, your answer is literally just going to be, is it guaranteed to be possible? Well, I mean, guaranteed to be possible because you got to jump all the way back to the front and do it. So essentially, oh, and then I guess the one from 0 to whatever is also counts as a gap. So Oh, so I guess gap plus 1. And we basically, that means we had to take out, we don't have, wait, what? Well, yeah, if you count this as a gap, then yeah, it is gaps plus 1, okay. So essentially you just take the sum of the g minus k plus 1's biggest gaps, and you just sum that up and add that to 12 times however many like segments you have. Okay, so let us code that up. What are we gonna call it? What do we call it? Zodiac Silver. Okay, using namespace int n comma k. All right, and we got our vector, or we could just do an array. So int what years 100,000. Okay. Okay, and then we also want a set of the segments, right? So essentially a segment is just 12-year segments, and we could just consider it to be the starting year of that segment. So we could have set int segments. Okay, and what else do we need? I think that's good for now. So we'll do cin n comma k, and then for int I equals 0, I less than n, I plus plus, cin years I. All right. So basically we want to we'll have our own comparison. Oh, we could do this. So we could do sort, which probably include algorithm. Sort years plus n comma greater int, like that. Okay. So now it is sorted backwards, and now we basically what is the formula? So if it is 96, then you want to divide by 12, and your answer is 6, and then that's the whole thing. Okay, so it is 96 minus 1 divided by 12 plus 1, right? Okay, so then we'll go through the years. Actually, we don't even need to sort years yet. We only have to sort segments. So we'll go for, or actually we could just do it here. So over here we will do segments.insert years I minus 1 all over 12 plus 1. And then we'll just go for I in segments, cout I. So we should get 3 segments for our test case. For 8 and 9, that is correct, right? We want to go from 108, we have 96, and we have the 48, are the ones that we care about. And then we also want to have the gaps between them. So we will, oh, is this sorted already? What the heck? Seriously? Is it guaranteed to be sorted? Huh, really? Okay, let's try it. So let's do like 6, 3, 1, 13, are we gonna say 0, 12, 14, 24, 36, 72, 96. Okay, so I guess it's always in order. It's a sorted set. Oh, that's nice. Okay. So we're just gonna go through it, and we're gonna push our gaps here. Set int gaps, and we'll also push insert 2. So segments dot insert 2. 0, sorry. Okay, and our gaps are going to be, it should be the end, right? So our gaps are going to be gaps dot insert I, or we should have a prev, right? So int prev is equal to -1. If prev equal -1, then we just want to continue. Otherwise, we do I minus prev plus 1, and then times 12. Oh, we don't even need the times 12. Okay. Alright, and then prev is equal to I. And then we need the int gaps to remove, right? So how many do we need to remove? It's just gaps dot size plus 1 minus what? K. Okay. And then we just go through for int I equals 0, or well, okay. So for int I in gaps, if to remove is to remove equals 0, then we want to return, or no, break. Otherwise, we want to have a total, int total, plus equals I to remove minus, and then our final answer is just going to be cout segments dot size plus gaps, and then times 12. Whoops, tote is what we want to add. Okay. All right, let's try this. 48. What did we do? So tot should equal 0. Segments. Oh, it should be. Wait, what? Segments is 3, so it should be 36. Tot should be 0. Oh. Okay, I'm being bad. Okay. So we need this. I'm trolling. If it's not equal to -1, then we do that, and we put this at the bottom, and we should be good. Okay. Okay. So gaps dot size is 2, which means that we only need. Why is gaps dot size 2? 0489. I don't want, yeah, we can't have a set. That, yeah, okay, I'm trolling. So, we want vector int pushback, and we'll just do gaps.sort, gaps.begin, gaps.end, and now we could literally just do this easier. For int I equals 0, I is less than 2 remove, I plus plus, tot plus equals gaps I. So 2 remove is 1, which is correct. And what are the gaps though? What? Okay, minus 1. Oh, I see. Okay, that makes so much more sense. Okay. And over here we should do minus 1. Okay, there we go. Now it should be working. Let us get rid of all this nonsense and submit. Hey, very epic. Okay, that one was a lot better. Okay. Nice, nice. Now we can move on to problem number 3. Very epic. Just green enough. Farmer John's pasture can be regarded as an n by n grid of 1. Oh, wow. N is tiny. What the heck? Of square cells, okay, of grass. Alright. We got another chessboard problem. Very nice. Due to soil variability, the grass in some cells is greener, okay, and is described by an integer level of greenness. Okay. So he wants to take a photograph of a subgrid of his pasture. He wants to make sure it is sufficiently green, but not ridiculously green. So for which the minimum value is exactly 100. So how many different photographs you could possibly take? There are n squared. Yeah, okay, that's right. And okay. So 500. How much can we do with 500? I'm assuming we can only do cubed, right? Because if you do cubed, you get 125 times. Yeah, okay. So we can do n cubed, I'm assuming. So we essentially got a grid of greenness. So let's try it with this. It is a square grid of greenness, alright, like that. And we got 57, 120, 87, 200, 100, 150, 141, 135. Okay. So essentially you need your subgrid to have at least one 100, and you need to have stuff that isn't less than. There's like stuff that you can't include. So basically you can't include this, you can't include this, and you have to include that. Although there might be multiple of them that you could include. Okay, so why don't we set like the topmost bar, right? And the leftmost bar. Okay, so for this one, this clearly doesn't work because it's guaranteed to include that, so we had to move over our leftmost bar, and we know that for this one, in order to include the 100, we need to at least bring it down to here, right? So anything like outside of this will work, right? So how do we quickly count to that? Well, basically our endpoint could be anything like to the right, right? So we can have like 1, 2, 3, 4. So there's 4 ways to do that. Then we move over here, right? Then there's no ways to do that because there's no way to get 100 in there. All right. Then over here, we know that our bottom bar has to at least be above here, right? Otherwise, it's going to include this. And we know that our bottom right corner has to be here or here. So that's +2. Then we move it over. We could do anything for these 4, right? So that's +4 again. Then over here, we can't do anything. And then we go here, impossible, here, impossible, here, impossible. So our answer is just equal to 10. Nope. What? What did we do wrong? So I said 2 over here. So we gotta have this and that, right? Oh, there's a 14 here. Okay, okay. That changes things. So essentially that gets rid of 2 from our first one. So that's 2 plus 2 plus 4. Okay, makes sense. So how do you know when a 100 is in your grasp? Well, okay, so basically your bottom. Okay, so let's see. Okay, so essentially your bottom is like blocked by the topmost cutout guy, right? And your rightmost one is cut out by the rightmost, like there, so I guess it's just there, right? Or like leftmost one. And then your like the upper bound, so this is the lower bound, and then the upper bound is just the closest 100s. Okay. Wait, that's kind of annoying though, because you might have multiple 100s, and then it is weird. Oh, let's see. Could we like do this kind of recursively then maybe? Okay, so if we know that like anything starting on this corner will have 100, right? But we had to deal with these dudes. Well, okay, so every subrectangle is defined by like a top point and a bottom point, right? Okay. And the reason why this is true is just n choose 2 squared. All right. So I kind of like my idea of like you fix a top right corner and then you find out where your bottom right corner can go. Could you binary search or something? Like, huh. Well, yeah, you could kind of binary search if you do like double prefix sums, right? So like you could keep track of how many guys there are, like for each how many dark ones there are. Let's see, but that matters. Well, let's see. Okay, so if we could somehow keep track of how many guys there are up here, right? how many guys are down. Oh, this seems kind of complicated. I don't think it's gonna be that complicated, right? Huh, so what else could we do? Huh, that's a good question, bruh. Okay, let's see. So we put it here. We know that's not gonna work. Okay, we put it here. Then essentially, how do we figure out where our next corner can be? So we basically have like two competing things. We have to include some things, at least one of one thing, but you can't include any of the other things. Okay, so how do we quickly find like how many are on the top left of this? Okay, so we could keep track of everything. Okay, so we could just define it recursively, right? So if there's one guy on the top left here and one guy on the top left here, then there's like two cases, either here, huh? Oh, but then we also know that this guy has one over there. All right. So recursively, we could find that the number of guys top left of here is whether like if this guy is dark, then it's like number of guys in here plus number of guys in here minus number of guys in there plus like 1, right? Or plus 0 if this guy is not bad. So essentially it's pretty easy to find how many number of things are in top left. Then how do you get, well, if you want in any specific range, then you just subtract here, subtract there, and add there. Okay. So essentially you just want the biggest one that works such that you don't get any new ones. So this one's going to be constant, right? And then you could binary search vertically and binary search horizontally, right? I don't know. Oh, well, I guess that doesn't really work. Since you might have like, I don't know, let's see. Well, we don't even need the number. The numbers are kind of irrelevant. So we can have like a dark thing here, right? Dark thing there. And we could have a dark thing there, right? So essentially we could go like here, right? Any of these, we could go any of these, and we could literally go any of these too. Assuming there's like 100 somewhere there. Huh, so why don't we start, okay, why don't we just start like going left to right, right? So essentially, does this contain 100? No, it doesn't. Then we go right 1, right? And then essentially, we had to check if there was 100 anywhere here. But we could just do that using like our like recursive thing, okay? So we could check that pretty fast that there's 100 there, right? And then essentially we could go here, and then we're like, we have to move up until we don't have any more of these black areas, right? Okay. And then you move over here, then there are no more black areas, so that's fine. Then here, you gotta move up until there are no black areas above here, right? So then you go there, okay. And then you just get, like, whatever plus whatever, and you just check if it has 100 in it. Oh, okay, that works perfectly well. Okay, let's do it. that works, okay. So now the strategy is you keep track of how many hundreds there are, like above, like within some box, right? Using that like cool recursive strategy we had, right? And then you can do the same thing for like this box, right? And then you keep moving this vertex, this bottom vertex up until there's 0, like of these dark boxes in it. Okay, so what are we gonna call this dude? Green enough. Green enough. Let's do it. Good stuff. Okay, so first thing we gotta do is we gotta read in our stuff. Int n, alright, and we got our int grid, and it's going to be 1000 by 1000 for the fun of it. Then we cin n, and we're just going to have, I don't think this really counts as DP. Does it really count as DP? I don't know. I feel like this might be a bit too complicated for silver though, right? Is it really going to ask me to do DP? Huh. But honestly, I don't really see an easier way to do it. Or wait, there might be an easier way to do it. Let's see. So I guess each column we could like keep track of where the earliest 100 is, right? Like, and if there's no 100, you just set that a -1, right? Then we go to here, then we know that the earliest 100, let's say, is over here, right? And the earliest dark thing is over here. And then you just have to jump this up to the earliest one, right? And then it has to be below the earliest 100, right? And then, like, you can keep track of where your current 100 is, right? Your current topmost 100. And then, like, for example, if you're, like, for this one, if there are no 100s here, then you know that since this 100 is below there, it can't be. Oh, wait. Okay, that's a lot better. Okay, that's kind of smart. So, we only had to keep track of, like, top 100 and top dark. Top 100 and top dark. Okay, and essentially we'll go through it for int I equals 0, I less than n, I equals plus, int j equals 0, j less than n, j equals plus, cin grid ij. And then, if grid ij equals 100, then we set top 100 for each column, which is symbolized by j, is equal to min of top 100 j, comma I. Very nice. If grid ij is less than 100, then we want to do the same thing but for top dark. Okay, so before this we should probably set it to a big number. Top 100 I is equal to 1000 and top 100 j is equal to 1000. Top dark. Okay, so now we basically fixed the top left point, right? For int I equals 0, I less than j, and I plus plus, and for int j equals 0, j less than n, j plus plus, and we're gonna keep track of our top. Let's just call it top for now, and it'll start off at 1000, right? So now we will go through the columns, right? So for int c is equal to 0, c is less than n, c plus plus. So we also have to keep track of our total. So int top equals 0. So top is going to equal the min of like top 100c and top. Okay. Oh yeah. Okay. We'll just have top top 100 and then top dark too for our thing. And then we'll have top h is equal to this, and we'll have our top dark is equal to that. So if our top h is like so if our top h, right, is here and our top dark is here, so essentially the top h is less than the top dark, then we have like however many are like between here and here, right? So obviously in this case there's only one, right? You have to do this, right? Okay. So if top h is less than top dark, we just do top d. We just do tot plus equals top d minus top h. And then at the very end, we just see out tot, and we should be good. Wait, that's kind of a big brain algorithm. Holy moly, dude. And nope, if it doesn't work, it's not a big brain though. Hold up. So let's see out top h, see out base, and then top 1000 0. What? What? Oh, bruh. Bruh. Okay. So it also means like underneath a certain point, we need the top dark underneath a certain point. Oh, bruh. Okay. So that's slightly different. Because we don't care. Okay, so if you have something here, we don't care about anything above it, right? So we also have to like say below a certain point. So we'll say 1000. Okay. So basically, just go through for int k equals I, k is less than n, k plus plus. We will say it's top k j and top dark kj. Okay, and then we should probably do the same thing here. Whoops, what? Top 100. Oh, whoops. KC. Or it should be I. Okay. Oh, it should be from 0 to I. Oh, okay, that makes a bit more sense. We only care about K from 0 to I. Alright. Less than equal to I. Okay, so now we're getting somewhere. So, let's see. So on the top row is 0, 1000, 0. Then on the next one is 0, 1000, 0, right? Well, so we also need... Oh, okay, so C is a J, it starts with J. Okay. Okay, so we got 0, 1000, 0, right? Oh, we just set it to N originally. Because if you have your thing at 2, then you could basically do 2 or... Okay, that makes sense. Alright. Hey, very nice. Okay, now we're getting somewhere. Let's try this. This should work, although I've not tested it thoroughly, so we might have to do some debugging after this. Alright, moment of truth. Let's see this. There's no way it's gonna work. I'm pretty sure we did not test this very thoroughly. Come on, man. I don't want to wait for the available grading server for eons. Come on, let's go. Bruh. Hey, very nice. Let's go. Finally. Okay. The first one went a bit rough, but the no, what? God dang it, what? Hold up. Oh, long. Okay, we're chilling. Oh, I would have been so triggered if that was... Okay, we're chilling. We are chilling. But dang, the first one was so triggering, but the rest... Okay, you know, that is why you don't use Python on Silver, okay? If you're using Python or Java, switch to C++ right now. This is like the best advertisement you're gonna get for C++. Holy moly. Alrighty, I think we will be good after this one. Alrighty, that is all we got for today. Thank you guys so much for watching. As always, if you enjoyed the video, leave a like and subscribe for more. I'm not gonna lie, the second two problems were kind of fun. The first one, I'm just a little bit triggered because I made so many stupid mistakes. But other than that, let me know what else you guys want to see in the comments. I hope this was helpful. Thank you guys again for watching, and see you guys next time.